While I'm sure you know this, you may have not have actually noticed that some things will heat up quicker than other things. Likewise, some things will take longer to cool down than other things. The reason why is because each substance has something very specific to it. It's a intrinsic property called the specific heat capacity of that particular substance. Now, what specific heat capacity is, like it tells you at the top of the screen, is the amount of energy that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So again, how much energy does it take to raise the temperature of 1 gram of a substance by 1 degree Celsius? Now, um, a very easy example of that is something with a very low specific heat capacity would be something like, say, the majority of the metals. Most metals, as you remember back in elementary school, when you slide on or you sit on that slide that's been sitting out in the sun, those things are extremely hot and they will burn your legs, right? Because they heat up very quickly. And then if you go to the same slide later in the evening, it might actually be very, very cold. It might be very chilly on your legs because metals tend to heat up very quickly and cool down very quickly. Now, on the opposite end of the spectrum would be things like water, which is a very good example of something with a very high specific heat capacity. And what I mean by that is, again, it takes a lot of energy in order to heat up water, and you have to lose a lot of energy in order to cool down water. It takes a long time. So again, another real world example would be like in the kitchen. If you have a pot of water, you turn the flame on underneath and your stove is on and you're heating up that water. If you were to touch, after a few seconds, if you were able to touch the side of the pot, you'd probably burn your hand. But if you dipped your finger in the water, it probably isn't even all that hot yet. Now, obviously it will boil and it will get extremely hot. But my point is after, just a short amount of time, the pot is already hot, yet the water is not yet. It goes again the other direction. So if I was going to take a piece of metal and water and heat them up to the exact same temperature and put them both in a container on my countertop, well, the metal would cool down much quicker. Meanwhile, the water would retain that heat for quite a bit of time and take a much longer time for it to cool down. Because again, water resists a change in temperature. Metals change temperature very quickly. And in a real world example, this is also true for our weather. One of the reasons why we get winds and storms is because the differential heating of the oceans versus the continents. The oceans, again, will retain heat and they'll stay a very temperate, consistent temperature through night and daytime, whereas in the daytime, the rocks and the land and the concrete all heats up a lot, and at night it cools down. And so that creates a very differential change in temperature, which does create the winds that we see on a daily basis. So all of this is very relevant to our daily lives. But now we're just going to do a little bit of math and try to actually calculate and understand this on a deeper level. So as you can see at the very top of your screen, specific heat capacity, we use the lowercase letter c, not the capital letter C, because that, of course, is carbon, the element carbon, and degree C is Celsius. So to prevent confusion, we use a lowercase c, which stands for specific heat capacity. Now, specific heat capacity has a very funny looking unit. It's joules per gram degree Celsius. So joules, remember, is a unit of energy per 1 gram per 1 degree Celsius. So that's why the gram and the degree Celsius are both in the bottom, because it's for each 1 gram for each 1 degree Celsius. Again, that is shown to you right there. So for water, again, we have a very unique number, which you'll probably end up memorizing. It is provided to you on the formula chart, but the specific capacity of water is 4.184 joules per gram degree Celsius, one of the highest specific capacities on Earth. There's only, I believe, one other substance that has a specific capacity that's greater than water. So again, to put that in regular English, water really resists a change in temperature more than almost anything else. So for number one, we're going to talk about the equation. The equation is Q equals MC delta T. Q equals MC delta T. So we need to understand what the heck does all that mean. So Q equals M times C times delta T. So I'm going to go into this in a different color. So Q stands for heat energy or thermal energy. M stands for mass. C stands for specific heat. I'm going to try to squeeze this in real small. Specific heat capacity. which again is the resistance to change, or more appropriately, the amount of energy it requires to change the temperature of 1 degree or 1 gram by 1 degree Celsius. And then delta T, of course, is a change in temperature. And that is going to, again, is going to be in degrees Celsius. All right, now what we also need to know is what are the units for these particular things. So heat energy in this context is measured in joules. Mass must be in grams. Specific heat capacity is joules per gram degree Celsius. And degree or change in temperature, again, like I just mentioned to you, has to be in degrees Celsius, okay? So the green is the equation, the blue is what they represent, and then the maroon is the units that are associated for each variable, okay? So that's the way that works. Now, let's go ahead and try this in an actual practice problem. So for number 1, what we have here is calculate the heat required. Heat, remember, is going to be measured in joules as Q, required to warm this many grams of water, or centigrams, I should say. That's going to be your mass. And then this, of course, is going to be your delta T. So Q equals MC delta T. So Q, we do not know. Mass, we need to have in grams. So in grams, so if I have 750 centigrams, for every 100 centigrams, I have 1 gram. So basically, I'm going to move. Ultimately, it's going to be 0.75. No, 7.5, excuse me. I'm going to move the decimal 2 spots to the left. So 7.5 grams. Again, just to show you, that would be 1 spot, 2 spots to the left, because again, we have 2 zeros. That's why. So 7.5 grams. 7.5 grams. Again, they tell us it's for water, so therefore it's going to be 4.184 joules per gram degree Celsius. Again, that is a constant for water. And then finally, my change in temperature. So 80, I'm going to do this as 80 minus 10, which would give me 70 degrees. Why did I do final minus initial temperature? Because if I do 10 minus 80, that would be a negative change. And my change in temperature is getting hotter. It's going from 10 up to 80. Therefore, that would be a positive change in temperature. So it needs to be 70, not negative 70. So you always want to do your final temperature minus your initial temperature, okay? That's important. All right, so all of this, again, is going to be very easy to calculate because I'm just going to multiply those 3 things together. So I got my calculator, 7.5 times 4.184 times 70, positive 70, gives me 2,196.6 joules. Why did I know it's joules? Because we're looking for Q, and Q is always measured in joules. So that's the amount of energy. Notice it's a positive value, positive 2,196. Again, that's not surprising because remember our temperature increased as a positive 60. If the temperature dropped by 70, then I said 60, excuse me, 70. If the temperature dropped by 70, then my Q would need to be a negative value because it would have been a loss of energy. All right, let's go ahead and try number 3. Number 3 is determine the specific capacity. Okay, that's interesting because typically, again, they would not ask us to solve that because, again, if it was for water, we already know the specific capacity. So for number 3, clearly, we don't know the substance. Determine the specific heat capacity, excuse me, of 10 grams of an unknown substance if 20.4 joules, notice it's a positive 24 joules of heat, are released, when lowering its temperature from 42 to 35 degrees Celsius. Okay, so there's a little bit of an interesting thing in here, but I know that my equation is this right here. That's a delta, sorry. My Q is my heat, so that is 20.4 joules. Now, because it is released and the temperature is lowered, that means this needs to be a negative value. Okay, if we are releasing heat, then the change in heat, which is your Q, must be a negative value. So it's negative 20.4, even though it shows it as a positive, because remember, it is being released. If we were absorbing heat, then of course it would be a positive value, like number 2. So that's going to be a negative 20.4 joules equals my mass, which again is 10 grams. My C is an unknown, that's my X. And then my temperature again is going to be 35. My final temperature minus my initial temperature would get me what? That would be negative 7 degrees Celsius. Negative 7 degrees Celsius. All right, so when I solve this, I'm going to go ahead and again, move everything on the right next to my C. Let me just go ahead and show you guys, just in case algebra is not your strong suit. I'm gonna go ahead and divide both sides by 10 grams and by negative 7 degrees Celsius. Cancel, cancel, which will move this all under here, 10 grams and negative 7 degrees Celsius, okay? So that will cancel out this and that, and this will cancel out with this, leaving all of this equals C. I'm just gonna go ahead and rewrite that C, just to make it look a little bit cleaner, equals C. Therefore, C equals negative 20.4 divided by 10, divide again by negative 7, and I get my answer of 0.29. Okay, now I need to know what my unit is for C. I already told you at the very beginning of the video, but if you notice over here, none of these cancel out. I have joules, I have grams, and I have degrees Celsius. None of that cancels out, so they all remain. Joules per gram degree Celsius. That's the specific heat capacity of this particular substance. Now, the fact that it's so low, 0.29, tells me that it heats up very quickly and it must cool down equally just as quickly. So that is a much, much, much more quick to heat substance, or a substance that doesn't resist change nearly as much as something like water. All right, let's go ahead and try the next one. Number 4. So number 4, it says calculate the mass. So calculate the mass of water of this many kilojoules of heat is absorbed or released. Oh, required. Why I said released? Excuse me, I totally misread that. Required to raise the temperature from 35 to 45 degrees Celsius. Okay, so we know the equation is Q equals MC delta T. That's an M. So Q is going to be this, because that's my kilojoules, but I need that to be in joules. So I'm going to move the decimal 3 spots to the right. So that'd be 9,750 joules. Again, I just moved the decimal 1, 2, 3 spots to the right. Okay, again, it is absorbed, so that's going to be a positive value because it is absorbed. All right, then my mass, well, we don't know the mass because they want us to calculate the mass. They do tell us that it's water, so that's going to be 4.184 joules per gram degrees Celsius. And then my temperature change again is 45 minus my initial temperature, which would be a positive 10 degrees Celsius. 10 degrees Celsius. Again, that has to match this because otherwise we're going to get the wrong sign. So again, I'm going to take everything next to my M or my X, if you will, divide both sides by it. Again, this is just basic algebra right now. Divide this by 10 degrees Celsius as well. And you guessed it, I'm going to do the exact same thing over here. Now, obviously, I don't expect you to always show this on your paper, but I'm just doing it to make sure you guys all understand exactly what the heck I'm doing. All right, so that will cancel out this, that will cancel out that. So let me go ahead and just get it out of the way. That way it's not confusing or distracting. So what we're left with is all of that equals mass, or M. So my mass is going to equal 9,750 divided by 4.184, divide again by 10. Notice I didn't multiply by 10, I divided by 10 because it's on the bottom. That would equal 233.03 grams. How did I know it's already going to be grams? Because of this. Because of that, my mass unit will automatically already be in grams. All right, guys, that's 4 very different problems involving specific heat capacity. It's the exact same equation. We're just looking for something different in each of these particular 4 questions, but it's all, again, the same concept. Q is the amount of energy put in or absorbed, which would be positive. The amount of energy lost would be negative. Mass has to be in grams. C is the specific heat capacity, which is the resistance of change, or the amount of energy required to change the temperature of a substance by 1 degree. Again, that if it's water, it's 4.184 joules per gram degree Celsius. That's a constant. And then your change in temperature, which you always do the final temperature minus the initial temperature, never the other way around. Otherwise, you'll have the wrong sign, positive or negative, right? All right, now that we have done all of this, we have just 2 more problems to try, because what we're going to do here is we are given a table. And in this table, we are given a whole bunch of known specific heat capacities. And we're going to have to try to figure out which of these is the identity of the substance based on these questions. So let's try it. So for number 5, it says we have a 55-gram sample of a metal at 90 degrees Celsius is dropped into a container of 250 grams of water at 22 degrees Celsius. The final temperature is 23.4 degrees Celsius. What is the metal? So you guys already know it's Q equals MC delta T. So Q, let's see. I am not seeing the Q. All right, so because it says at the top of the screen that the amount of heat lost is equal to the amount of heat gained, we're basically going to put 2 equations kind of together. So this equation, as we see right here, is not exactly what we want to do. There is no Q, which it took me a second to figure that out. Sorry about that, guys, for the pause. That's what I was doing as I was trying to think this through. We're going to go ahead and put the 2 equations together. So for example, this would be our metal, and this one here will be for the water. Because as you'll notice, we have in the question, we have amount of grams of a metal and the temperature at which that metal's at. Then it's going to be dropped into a container at a different mass and a different temperature. So we're going to set those 2 together. We know that the C for the water is 4.184. Therefore, we have everything we need except, again, if this is going to be the metal and if this is going to be the water, the only thing we don't know is this unit right there. We have everything else. All right, so let's go ahead and try to fill this in. I'm gonna go ahead and erase this to just give myself a little bit more space. All right, so let's go ahead and do the water first on the left. Now, again, it makes no difference. Actually, yeah. Just to keep it consistent, I'm gonna go ahead and do the water first on the left side. So the mass, again, we know is 250 grams of water. The specific capacity is 4.184 joules per gram degree Celsius, because again, it's a constant. Now, the temperature of the water is at 22 degrees. So 22 degrees. The final temperature is 23.4. Oops, I did that backwards. Look at me making a mistake already. Final minus initial, 23.4 minus my initial. That would give me what? 1.2 degrees Celsius. Yep, 1.2 degrees Celsius. So again, this is for my water only. Now I'm gonna do the same thing, but now for my metal. So the metal we have is a mass of 55 grams. The specific capacity, again, is our unknown. And the change, it went from 90 degrees. And then it is, the final temperature is 23.4. So 23.4 final minus initial. Always final minus initial. I know it sounds weird, but trust me, that's the right. Minus 90 gives me a negative, again, not surprising because the metal was very hot, 90 degrees Celsius, and it gets cooled off as it gets dropped into the water. So it's not surprising. This is a negative 66.6 degrees Celsius. So negative 66.6 degrees Celsius. And again, just to recap, this is for our unknown metal. All right, now that we know all that, what we're going to do, of course, is solve for C. So I'm not going to write all of this out because that would be a little bit tedious, but I'm going to move all of this stuff here next to my C, and I'm going to move it down under here, right? So I'm just going to go ahead and just do this only. Again, that will cancel out this. And I'm going to do this one over here, 66.6 degrees Celsius. And again, that will cancel out that. So let me just rewrite this right side to make it a little bit cleaner. That's going to equal C. All right, so 250 times 4.184 times 1.2, because they're all on the top and multiplying all of them. I'm going to divide by both numbers on the bottom, divide by 55, divide again by negative 66.6 equals why is this negative? 342 joules per gram degrees Celsius. Came out to be negative, and I'm not really sure why, because that won't make any sense. So in this particular case, let's see, it looking like most similar to copper, but I would expect it to be a little bit nicer than that. Final minus initial. Final minus initial. 1.2, negative 66. The water gets hotter. The metal gets colder. So it would be negative 3.42. Interesting. Well, let's try the next one. That's a little bit unexpected. All right, so again, we're going to do the same thing here. We have a 200-gram sample of a metal at 92 degrees Celsius is dropped into a container of 100 grams of water at 26 degrees Celsius. The final temperature for both of them is going to be 45.6. So again, just to keep consistency, even though it makes no difference which side I put the water, which side I put the metal on, but just to be consistent, I'm going to go ahead and put the water on the left. So my mass times specific capacity times the change in temperature is equal to the amount of heat lost, which would be M times C times delta T. So my mass of my water is going to be 100 grams. And of course it's water, so it's 4.184 joules per gram degrees Celsius. And then my change in temperature, so the final temperature is 45.6 minus my initial temperature of water, which is 26. I'm going to go ahead and do this on my calculator just so I don't make a mistake. Okay, is 45.6 minus 26, which is 19.6 degrees Celsius. 19.6 degrees Celsius equals, now moving to my metal, I have 200 grams of metal, a lot more compared to the water, but whatever. Our unknown specific capacity, and then the temperature for the metal is going to go from final minus initial. So final is 45.6 minus my initial temperature of the metal. Again, so it's going to be another negative number. 45.6 minus 92 would be a negative, because of course the metal is going to cool off. 46.4, negative 46.4 degrees Celsius. So again, I'm going to do the same thing I did on number 5. I'm going to take the two numbers on the right, slide them underneath the left side. So that would be 100 times 4.184 times 19.6 equals this, divided by 200. Divide again by negative 46.4. And what I get for my C is negative 0.88 joules per gram degree Celsius. So 0.88 is as close as we can get to aluminum. Not exact, but it's pretty close. Now, again, I'm a little puzzled why those aren't more precise, but the setup is correct. So again, thank you guys for watching. This again, for number 5 and 6, why this is different from number 1, 2, 3, and 4, just so you guys are clear, is that when we have two things interacting, in this case, some unknown metal and the water, the amount of energy that's going to be lost by the metal as it heats up the water will be exactly equal to the amount of energy gained by the water as it cools down the metal. So they are equal to each other. So that's why I set them equal to each other. There is no Q because they just go from one to the next. All right, guys, thanks again for watching. Let me know if you have any questions.